Hello, everybody, and welcome to another lecture of 6837. Today, we're going to begin our transition in this course from talking about geometry, transformations, that sort of thing, into the next segment of 6837, which is to talk about motion and animation. So today, we'll cover some high-level ideas about the animation universe and talk about one particular technique called skinning, which is particularly useful for animation techniques, especially with animated 3D characters. So one of the really cool things about computer animation is that it has its history in the hand-drawn animation or traditional animation universe. So in fact, when we take a look at different algorithms for animating characters and how we store that information, edit it, process it in graphic software, and so on, a lot of it really does have its history in how people used to produce, or I suppose can still produce, hand-drawn animation techniques. So here we see an image of a person drawing Mickey Mouse. And they're following a pretty typical method for doing so, which is to decompose a given scene, in this case for 2D animation, into different layers or cells that get composited together on a background plate. You can get lost in digging through all kinds of ridiculously cool technology that people invented to make the animation process simpler. As you can imagine, it's extremely painstaking to make a hand-drawn animation. I can't say that I ever have beyond, like a little flip book in elementary school. But essentially, if your animated film is upwards of, 20, 30 frames a second, in the worst case, that's 20 to 30 drawings that you have to produce to get a single second of animated content. So it's just amazing, the technology and the techniques that were invented in the non-computer animated universe to make that process feasible and to see how it's evolved over the years. There's so many clever ideas here that are worth mentioning because they appear in the computer graphics universe as well. One of the basic ideas in hand-drawn animation is the idea of making keyframes and then in-betweening. The phrase in-betweening is kind of a verb in computer graphics and animation. And the basic point here is that a very typical way to save time for maybe the senior animator would be to just draw the kind of major keyframes that are separated by big chunks of time in the animated sequence. And then you would hire maybe a more junior animator to do a task called in-betweening, which I can only imagine has got to be really tedious. Basically, it involves drawing all of the intermediate frames between the keyframes that the animator drew. Notice that this already has some commonalities with how we've talked about splines and curves in this class, right? Our splines were defined at these isolated control points or knots, and then we had technology that we developed over the last few weeks that allow us to interpolate information in between. So in some sense, the people doing in-betweening are like really fancy human AI, spline techniques for animated data. But celluloid animation really goes beyond just that one, insight. There are all kinds of clever ideas. Another one is when you watch these Disney movies and the camera kind of zooms in and out. One of the ways that they could do that was by drawing an object like a multi-perspective panorama, which is shown on the screen here, where obviously, when we view the entire panorama in one shot, it doesn't look like a photograph of a 3D scene, but this is sort of optimized so that when you view just a piece and you scroll through, it gives you the illusion of maybe panning across the scene, zooming in and out, and so on. And then finally, another technique that got invented in the cell animation world was to composite a scene together using layers and even multiplane cameras. So the different layers might be the different characters in the scene, drawn on some transparent material so that you can stack them on top of each other and see the whole scene composited together. And then a really clever technique, which was pioneered, I think, at Disney Corporation, is this idea of actually taking those planes and separating them vertically by putting a positive amount of space in them and then pointing a camera all the way down And then by changing the relative spacing between these different planes, you can actually get a 3D effect. Now in the slides, I've embedded a video of the multiplanar camera. I'm not going to play it here because we're on YouTube and I don't want the Disney Corporation to take down our graphics lecture, but I'll provide a link to this video in the notes, and I encourage you to watch it as a fun way to see some of the early technology. Now, essentially, if you look at the history of computer animation, starting in about the 1980s, Disney started to digitize their cell animation pipeline. And so a lot of these sort of golden era animated films were already made with some software tools called CAPS, which was essentially a piece of software that was actually made, I think by contract for Disney from the Pixar company, which may sound familiar. And the basic idea here was that they were translating all the steps of hand-drawn animation to the computerized regime. And the really beautiful thing that happened is that this was possible, and that actually the same techniques that people were using for drawing animated content seemed to work okay for computer animation as well. And of course, from there, the technology only got better, and some of the effects that were only possible in the digital world started to emerge. Again, in the slides, I've incorporated another sort of test video sequence from Disney, one of the early ones from Where the Wild Things Are. And I encourage you guys to watch it at home. I mean, one of the really amazing things you'll see about this sequence, this is from a relatively a long time ago by computer graphics terms. But if you saw it on TV today, I think you would think it was all right. So I think in some sense, the technology was pretty good from the start. What's improved over time, obviously, are a lot of details and different artist controllable, aspects of the look, simulation, and so on. And importantly, the computation speed that I'm betting the compute power that we would need today to put together the scene that's shown in this little video test that you should watch at home is, today we could do it probably in real time. The compute power back in the day using computers in the 80s and 90s was far less so. So a lot of these ideas were laid out in some early work, and really you'll recognize many of the names and companies that appear in these early research papers, software products, hardware products, and so on as big names in the movie industry. For instance, John Lasseter was one of the first employees at Pixar. More recently, he unfortunately was tied in with some more negative news. But in the computer graphics world, he wrote a sort of seminal piece of research that talks about how you can adapt a lot of the traditional animation principles to the 3D animation world, and that ideas like keyframing and in-betweening really clearly translate from the analog to the digital in a really beautiful fashion, and that these analogies are more or less what we're using today. Incidentally, if you like this kind of thing, there's a really cool book that I encourage everybody to take a look at, titled The Illusion of Life here. Sorry, I'm going to adjust my chair. Which sort of lays out some of these principles of the animated world. And what we'll see is that we can actually capture very rudimentary versions of this using some of the constructions like splines that we've already developed in this course. So the basic observation in works, which of course I'm going to dramatically oversimplify, but things like this book, is that the animated universe is totally different from the physical world around us. And that's true for any number of different reasons. So of course, it's the case that animated worlds look very different from photographs and so on. Actually, there's a really interesting philosophical question, which is that the modern computer graphics pipeline is largely built on simulating, the physics of light and materials, but then modern animated films don't really look like real life. You could ask a totally plausible question, which is, okay, so why do we bother? Maybe we should come up with like a totally cool non-photorealistic art look that has nothing to do with physics. But that aside, I think one of the really fascinating aspects beyond the look of old animated films, which I encourage you to go on a YouTube binge and watch, is actually the physical dynamics that appear in animated content. And one of the really neat observations is that the physics of the animated world, and of course they can vary from film to film or clip to clip, are often inconsistent with real life physics. I mean, they're not following F equals ma, but they are consistent with themselves, and they actually create their own physical universe that is probably tied together with the artist's vision of the world, aspects of the human visual system that we can try and exaggerate, and so on. So for example, two terms that you often see in the animation world are squash and stretch. And so these are sort of these phenomena where objects can squash and flatten in a really exaggerated fashion that makes no sense physically. So for example, take a look at the figure on the left here. So here we have a pretty typical animation of like a bouncing ball sequence. So maybe the ball is bouncing from left to right here. Now, and what we're showing in these like superposed little ellipses are just different points in time in our animation. Now, initially, I bet if you kind of glance at this animation, I think all of us would perceive it as an animated bouncing ball. But if we step back to philosophize a little bit about what's going on in this clip, things start to become pretty questionable from a physics perspective. So, for example, I think you would be hard pressed to find a bouncy ball that squashes as much as you see in this little sequence here. But maybe there's a material that does that, and then, somehow has a really good coefficient of restitution. So when it comes off of the ground, it totally restores back to its original shape. There's an even fishier aspect, which is, let's say that the plus t is going from left to right. This was actually looking closer. Maybe it goes from right to left because this is a little higher, but whatever. Take a look at this ellipse here. Notice that the ball lengthens in anticipation of hitting the ground. So that's not how physics works. If I drop a ball on the ground, the ball doesn't know it's going to hit the floor until it actually makes contact. But in this animated sequence, the ball actually gets a little bit longer, almost like it's stretching out to emphasize contrast with the squash that's about to happen when it hits onto the ground. This is non-physical, but the really beautiful observation is that it's often quite consistent in animated physics. And so these principles really informed how people did their artistic work in this area, and really it led to a particular look that I think we associate originally with hand-drawn animated films and now with computer animated films. Of course, what that meant is that the computer animation pipeline cannot be and should not be completely accurate from a physics perspective. We are in this class going to talk about physically based animation, but it's also important to note that the goal here is not necessarily to capture physics as accurately as possible. If you want to do that, you can, take our scientific computing courses. Rather, it's to get some idea of physics that communicates motion in an interesting and compelling way. There are all kinds of different examples of video game or not really, well, to some extent video game, more so in animation, the type of physics that can go on. Of course, there are other ones, like the timing can affect the weight and vice versa. Like light objects maybe move quickly, heavy objects move slower. If you recall, that's not how acceleration to gravity actually works, but it can communicate mass in a way that would be difficult to communicate using filmed content. And of course, animated characters tend to make extremely exaggerated motions and so on. I remember working with some colleagues at a computer graphics company that were trying to replicate the motion of an animated character in an actual physical robot. And very quickly they discovered that this really wasn't possible, that like a single motion of this character would like launch it off the ground and into space, because animated characters move in this extremely non-physical way. Of course, this also tells us a little bit something about how our brain works. I'm not a neurophysicist or whatever, but if you watch these animated films, you're perfectly happy to perceive characters moving in what almost feels like a physical fashion. But if you step back and start asking questions, it all comes apart. Okay. So, of course, in computer animation, to step back a little bit, is really the process of generating and describing motion in a scene, sometimes given keyframes. And there's a push-pull between physical accuracy, expressivity, and other aspects. And these are techniques that are enjoyed in all kinds of different contexts. One of the big luxuries in the film industry, for example, is that, of course, when we actually watch a film, it's not like we're doing the animation or the computer's doing the animation in real time, right? And so what that can allow us to do is to develop animated sequences computationally using much more time than it actually takes to play back the sequence. Because, like, so for example, in Pixar's Cars film, it could take up to 100 hours to generate a single frame of this animated sequence. And that's okay, because once it's generated, we store them and then we just play them back as a sequence of pictures, right? So, you know, if you crack open the DVD that you purchased with the Cars film on it, you won't be able to find the assets and the 3D characters that comprise that film. They're all flattened down to the image sequence. And so what that allows us to do, for example, is maybe the animators specify the primary motion in the scene, you know, like how the characters are interacting, moving around. And then maybe we also use an extremely fancy physical simulation tool that takes, 100 hours per frame to fill in the secondary motion and the smoke and the fire and composite all that stuff together. And that's perfectly fine. Of course, a contrasting scenario in the computer animation universe is in games. Now, in games, you have to produce frames minimally at 30 frames a second, or else your eye is going to perceive this little kind of blip in the motion. And typically games operate at a much higher frame rate than that, so that we can also afford computational time for just the game interaction, AI, and so on. So in that case, there's more of a push-pull, not just in terms of accuracy versus physics versus animator control, but also computation time, right? Because if any of your animated effects take more than the time it takes to perceive a frame, then your entire universe has been suspended, and the person playing the video game is reminded that they're not inside of the video game world, but rather that they're staring at a computer that just had a hiccup, which is not so good. So computer animation presents this huge host of challenges, both in terms of modeling and in terms of computation, right? On the modeling side, we want to expose to artists and end users and game players all of these different expressive ways of making motion. And then on the computational side, we actually have to generate and render that motion in an extremely small amount of time, especially in the case where we need real-time feedback, like in computer animation, or more recently in virtual reality. And so this is an extremely challenging area, and one that is full of active research and development. I mean, every year you can go to the SIGGRAPH conference and see all kinds of clever ideas for new methods for computer animation. So today we're going to talk a little bit about different types of animation, just so that you guys get an idea broadly of this area and some of the ways that you can control animation. And then we're going to talk about one particular technique called skinning, which is used to actually move animated characters around given coarse motions for their bones. So for example, if I have my arm here and I bend my arm, if your instructor were more in shape, you would see more interesting motion. But of course, I'm essentially controlling it by just a one-dimensional pivot about a point, but there's all kinds of motion happening, and including a smooth transition from my upper arm to my lower arm. And so the question is, how can we capture that without having to animate every single vertex of a triangle mesh independently? So let's get started. First, we'll talk about different types of animation, just to give you guys some basic vocabulary words when we talk about the animation universe. One type of animation, which is really critical, is called keyframing. This is something that I think is totally unsurprising given our discussion of splines already in this course. But essentially, keyframing, the idea would be that I specify my scene at a few isolated instances in time, and then the computer automatically generates the in-betweens. So for instance here, let's say that I'm animating a levitating bunny. Maybe what I would do is at 4 points in time, T1, T2, T3, and T4, I would specify the pose of the bunny. And then I would rely on in-betweening software to come up with, maybe somewhere over here is the position of my bunny at time T1 plus T2 divided by 2, or something like that. And so in some sense, we're relying on machinery like splines and cubic curves and so on as a replacement for that professional in-betweener. Not that we would ever want to put an animator out of a job. But in any event, beyond keyframing, there are other types of animation that are in the computer science universe worth knowing about. So another one is procedural animation. So in procedural animation, I write a piece of code that does the animation for me, and I try to express it as a relatively small number of parameters. So the classic example of procedural animation would be to animate, for example, a stopwatch, right? So maybe I animate the, I'm in Alice in Wonderland, my stopwatch is going crazy. I'm going to just animate it by specifying how the time changes. As a function of time. So to put it differently, the angle of the stopwatch. And then I've written a piece of code that takes these sort of abstract parameters and generates a stopwatch with all of its arms in the proper location specified by my piece of code. Right, so this is a little bit different from keyframed animation, right? The goal here is for the computer to take care of the animation given sort of high-level instruction. And so procedural animation is used all over the place. So for example, another place where procedural animation often appears is, like let's say that I'm making a film and I've got, two hordes of characters that are coming in and going to fight one another. Maybe I don't want to animate every single secondary character by hand. So I write some pieces of code that generate basic motions and then I set them loose. By the way, all of these animation techniques, there's extremely porous boundaries between them, right? I could keyframe a procedural animation, for example, and mix and match these different strategies in different fashions. Right. Oops. So other types of procedural animation, incidentally, can include some random number generators. So maybe I also incorporate in my procedural animation, like trees swaying or something. So later we'll talk about a technique called boids for simulating flocks of birds flying around. Maybe I generate the velocities randomly as the birds move. Different type of animation, which is extremely popular, especially among MIT students, is physically based animation. And this actually tries to bridge between the animated universe and the physical universe that we all know and love. So maybe we assign physical properties to the objects in our 3D scene, and then we solve Newton's laws, like F equals ma, and use the solution to those equations as our animated content. This is extremely important, especially for secondary motion inside of an animated scene. So for example, maybe my animators control the 3D characters that are interacting with one another inside of a animated sequence, but then the clothing that they're wearing is simulated using a physical tool rather than like keyframed, right? It would be pretty frustrating to have to keyframe the motion of your big drafty shirt as you're running around a scene, you're running around a kitchen or whatever. And so physically based animation often happens a little bit later in the computer graphics pipeline. So maybe I keyframe the basic motions and then I rely on my physics simulation tool to fill in some of the detail. And the reason for that is that physically based animation is realistic, kind of by construction. Doesn't have to be, by the way. You could invent your own physics laws if you wanted to. But it's hard to control, right? So for example, let's say I wanted to make an animated sequence where I have a big pile of rocks, I drop it on the ground and it spells out my name. I I would like that motion to look like things are falling and bouncing off of one another and so on. But if the artist really wants it to spell out my name when everything lands, it would be really hard to lay out all of the objects in your hand in such a way that that happens. That's a very difficult inverse problem, arguably impossible. And so physically based animation, the typical complaint is that you run your physical simulation, you don't like the way it looks or the way it interacts with your artistic content, then it's very difficult to revise or control. That said, some of the state-of-the-art techniques, even in physical simulation, which has many applications outside of computer graphics, originate in the graphics world. And there's some absolutely beautiful physical simulations out there of different physical effects. For instance, and I'll include links to all these videos because I'm not sure how well they'll be captured on OBS. A very typical and very exciting area to be in is in fluid simulation. At this point, to my eye, many of the physically based water simulations are really indistinguishable from reality, which is pretty exciting. And so, there's like endless content on YouTube you guys can all go watch of all the cool physically based animation that are just beautiful. And I think you see it especially in these blockbuster films. Another place where these things can appear sort of coupled sometimes with procedural animation is in characters. So one of the things that we probably don't think about a whole lot is that the way that we walk is obviously informed by physics quite a bit. That makes sense. And in a lot of scenes that are maybe really dynamical, like a character jumping over an object, you actually want to include a physically based sort of forcing factor to make the motion look more realistic. And so oftentimes people will use physically based animation in conjunction with their 3D characters to add aspects to the motion that look more realistic. So let's see if we can zoom forward a little bit in this clip, and we can see a person jumping over this little object here. And so these are examples where maybe I specify some high-level aspects of my animated sequence, and then all of these aspects that make the character look like they're landing on their feet really have to do with like motions of inertia and so on that would be difficult to capture manually in an animated sequence by hand. So there's all kinds of different ways to control animation, and this is really critical for a very similar reason to why we don't like to, for example, edit curves by editing every single vertex along a polyline, right? What we want are high-level controls of animation where the artist or the end user can specify the basics of the motion and then rely on the computer to fill in that secondary stuff that's less interesting to actually animate. And so the basic idea here is that animation is typically controlled using very low dimensional things rather than maybe the high dimensional data that's going into actually rendering your scene. So for example, maybe for most 3D characters, they're rendered at the end of the day as a triangle mesh composed of 100,000 triangles. Rather than animating the vertices of these triangle meshes all one at a time, we'll go to a lot of work to specify how those vertices move in response to different types of actuation. And this is really common. I mean, for example, if we're going to specify that little flying bunny scene, then we probably would draw a spline in the space of rigid motions rather than manually animating every single vertex of the bunny to move one by one. Or the really common one has to do with articulated characters. So the phrase articulation here refers to like being full of bones. So for example, human characters, like what we see on the bottom right, rather than just making a 3D model of their outer surface, a very typical thing to do is to also specify how that 3D model changes in response to different sort of high-level parameters, right? So a very typical thing to do would be to store the angles of the different joints on your animated character, and then to have code that essentially translates all of those joint angles into a pose of the character, so that, if I want to move my arm up and down, I can do that by just specifying this angle And all of the triangle mesh that's filling in the flesh in between is computed automatically here. Sorry for these boring motions in front of the camera. It's hard to do this sitting down. So essentially, when we talk about these different animation techniques, for now, we're going to focus largely on a piece of the pipeline that's known as maybe rigging. So far, our discussion in this course has largely been in modeling, right? We've talked about how to design a 3D model, store it on the computer, and control it using some high-level controls. There's a different process called rigging. And the idea of rigging is that it's not enough to just have a static pose of a character. We also want to give it some high-level controls over things like joint angles and so on, right? So the process of rigging is basically the process of specifying how a 3D character should change in response to these changes in parameters. Now, one of the interesting things is that terminology about rigging, 3D animation, and so on actually contains many commonalities with terminology about robotics. And that makes sense, right? If I make a robotic arm and I want to guess the position of the end effector, like the grasping thing all the way at the end of the arm, I need to be able to predict that position by knowing the angles of all the different actuators or joints that live above the end effector. So that process is known as forward kinematics. So in more detail, forward kinematics basically is telling you how to locate every body part position as a function of joint angles. That often basically requires you to compose together lots of transformations. So for example, maybe I have the angle of my shoulder, the angle of my bicep, my wrist angle, my finger angle. Now, if I want to know the position of my fingertip as an XYZ position, I have my body in some basic rest pose, is usually what it's called. Well, now when I bend my arm and my finger and my wrist, I have different angles and all of these things that essentially are inducing different rotation and translation matrices all the way up and down my kinematic chain. And so if I want the position of this fingertip, what we're going to see is that I've got to multiply all those matrices together. So that process is called forward kinematics. So given things like joint angles, the output of forward kinematics is the actual position or pose of the 3D character. There's a different procedure that we'll also talk about a little bit in this course. It's often a topic for our students' final presentations or projects, which is something called inverse kinematics, or IK if you're in the know. So in inverse kinematics, we do the opposite, which is I want to specify the location of something. Like I want to put my hand here. And then in the IK problem, it says, what joint angles do I need so that my hand ends up at a particular location? What we're going to see is that the forward kinematics problem is relatively easy computationally. And the IK problem, the inverse kinematics problem, is relatively difficult. It's going to require nonlinear optimization. So we're only going to touch on it in this course, and I'm more than happy to point you guys toward resources to tell you more. So during the forward kinematics procedure, typically, we have a fair number of bone angles, but it's far less than the number of vertices that are on the triangle mesh of the 3D character. Right? That's sort of the difference between this like blue guy, the blue man group here, who's expressed out of a few ellipses, and the 3D animated character that's sitting underneath him. And so what we need is a link between these two things, right? So in particular, if this blue skeleton moves, I need to figure out how the triangle mesh sitting underneath moves in response to that motion. And the way that we're going to do that is using a technique called skinning. And so skinning is basically the idea of writing down weights that are going to tell us the influence of each bone on the motion of each point on the outer surface. The process of actually doing your skinning is sometimes called binding, which makes sense because essentially what we're doing is binding the vertices to the motion of different bones, although we're going to see that we can do that with a weighted average to get a kind of smooth skinning effect. And so at the end of the day, our goal here is that we want to animate the motion of the skeleton, and then the skin is going to move along with it. So notice that exactly falls into the setup that we've talked about, right? We want the artist to control something high level, like the motion of the skeleton, and then the computer takes care of moving all the millions of vertices that are living in the underlying triangle mesh. Now, in terms of those high-level controls, there are many ways to do it, right? The artist could control the motion. A different technique is to use something called motion capture. It used to be that we did motion capture using all kinds of little markers that we might place on a character. As you can imagine, it's quite difficult to convince, Brad Pitt to put all this uncomfortable stuff on before they do their acting. So more recent research has focused on a technique called markerless motion capture that tries to do it without all of these bright lights being attached to your character. This is particularly important for if I want to do motion capture, but for like stunts and so on, where it might be difficult to have all this stuff connected to your body and get all the motion that you need. So the motion capture idea here is that I attach lots of optical markers. They don't have to be optical, I suppose, to the character. And in this case, I really mean like an actor in world space. The actor moves around. We use computer vision technology, which incidentally has gotten a heck of a lot better in the last couple of years, to track the marker positions. And then we project that marker motion onto the motion of the animated character. So for example, DreamWorks is an animation studio that I believe uses motion capture quite a bit. And in some sense, it's a very efficient way to animate, right? You can get really subtle nuance and realism because essentially you're just borrowing it from actual human actors. On the other hand, some animation studios really don't like the motion capture, or I should say some animators. So Pixar is typically a studio that's associated with this, where by using motion capture technology, you're also constraining your animation in some sense, right? Because of course the motion that you get out of motion capture came from the physical world, right? Animated characters are not constrained by physics. So essentially by using mocap, you might not get some of the special secondary crazy motion that the animated world allows that physical humans or actors really couldn't carry out. That said, there's all kinds of cool motion capture. It changes all the time. I have some videos in the slides which are already outdated, but this gives you some idea of what goes on in this technology. So here's a human actor with markers on her face, and we're seeing that essentially by tracking those markers, we can put them on a animated character. These days, I don't think we even need the markers. That modern deep networks, computer vision technology has made some of that marker stuff irrelevant, which is good because it's really difficult to set up. Of course, the computer vision problem, if you don't have markers that somebody has painstakingly placed on your character, is much harder. Regardless of whether you have markers or not, there's a useful vocabulary word here called retargeting. And this is the procedure of taking the pose of the person that you are capturing with your camera and then retargeting it to your animated character. This can be pretty tricky, right? Because typically we're not using mocap to just control a 3D model of ourselves. Sometimes we are, but typically not. Typically we're using motion capture to control a character like Shrek or something. But of course, their motions are very different than the motions of a human. So there's some retargeting procedure that has to not just apply 3D transformations to your pose in space, but also maybe constrain the motion in different ways than the human actor that you use to record. So this is a really tricky and painstaking process. By no means is mocap somehow a totally easy way out of the animation process. It's just a different technique with its own headaches. So at the end of the day, this allows us to do all kinds of cool things. Like here's a research paper from a few years back. In this case, it's markerless motion capture. So they didn't put a bunch of stuff all over the actor's face. You can see some pretty noisy signal here as the input to the camera. And he's able to control all kinds of funny characters here, not just a face, but also this little gooey green guy. Here's another example. Of course, one of the real triumphs of markerless motion capture in the last couple of years. This involves not only removing markers, but also retargeting, is that it allows Apple executives to control the turd emoji in real time. So it's pretty amazing that this technology has gone from placing markers all over an actor's face in a very careful fashion and synchronizing them with a computer to something that you can literally do with a device that fits in your pocket without any markers at all and can control a 3D poo. So in any event, I'll let you guys marvel at this technology on your phone on your own time. And of course, you're invited to share with the other students if you have any interesting and course appropriate motion capture animation. Of course, that's on the consumer end. There are many mistakes that can happen on your phone's motion capture that would not be acceptable in animated or filmed content. But really, the technology on the high end has advanced to the point where motion capture can be incorporated with animation and physical dynamics and so on to make really realistic scenes. So, for example, here's an image of the actor for Davy Jones, I think, in Pirates of the Caribbean. This was a human actor recorded in the scene with motion capture. And then, of course, in the video, in addition to some lighting changes, you can see that there's a composited on top of that actor, an animated character, which is combining the motions of that human actor with, I'm sure, some manually drawn animation as well. Okay, so anyway, this is obviously a very high-level discussion, but I just want to get you guys excited and thinking about all the possibilities of computer animation. It's a really great intersection of math, like physics, algorithms, and also artistic content. And there's no real winner here. All of these are needed to work in this particular area. Really exciting place to be. Okay, so for the remaining part of our lecture today, we're going to dive into one particular approach that's relevant to character animation, which is skinning. So the basic idea here is that from our previous lecture, we know how to animate a bone hierarchy. So for example, using some of the hierarchical modeling techniques that we've discussed in the previous lectures, if we know a kinematic chain of joint angles up and down a human character, we can compose all of those matrices together using the hierarchical modeling techniques to get a transformation that goes directly maybe from the end effector to the body or vice versa. Our next task in skinning is to do all that secondary motion. So if we know how to animate a bone hierarchy, we now embed that very coarse skeleton into a detailed triangle mesh, bind the skin vertices of the triangle mesh to the bones. And now when we animate the skeleton, we want the skin and bones to move synchronously with one another. Now there's many different techniques for skinning. There's, as with anything in computer animation, a big push-pull between physical plausibility, computation time, and so on. In this course and subsequently on your homework, we're going to cover a really simple technique, but it's also one of the more popular ones in practice. And if you look at the state-of-the-art skinning algorithms, they're not all that far away. They're kind of variations on the theme. Pardon me. So in order to do skinning, sometimes called enveloping or enveloping, I'm not sure, we need to infer how skin deforms given bone transformations. Of course, the reality is that it does that with physics. You know, we're all filled with, meat that is determining the dynamics of our body as we move around. But oftentimes, animated characters are basically hollow, right? They're just triangle meshes with no meat on the inside. And so we need to do something that makes for a plausible, but not necessarily physically accurate motion. Remember, in graphics, often we're just going for plausibility, not accuracy. And the most popular technique, I would argue, is something called skeletal subspace deformation, SSD, or sometimes we call it skinning. In fact, this is one of these ideas that's really natural and appears all over the place and with many different names like vertex blending, matrix palette skinning, linear blend skinning. All of these ideas are roughly isomorphic to one another. So in SSD, each bone basically defines a deformation of the space around it, right? So maybe, my rest pose is like this. I come up with some new pose. And now if I look at like just my upper arm, there's some rigid motion that goes from the pose of my upper arm to in the rest pose to the pose of the upper arm that I'm trying to actuate. And then what we're going to do is we're just going to apply exactly the same rigid motion that I used to move my bone to the skin that's close to that bone. And so if I stopped there, my skin would be kind of rigid, right? So for instance, maybe I represent my body using a triangle mesh, and every vertex is just attached to one bone. Like, this point is attached to the upper arm bone, this point is attached to my hand bone, and so on. But that can become problematic. So let's say that I have here's my arm, very roughly. It's two rectangles attached to one another. And I say that all of the vertices on the left-hand side in area 1 move with my upper arm. All the vertices in area 2 move with the lower arm. Here's my body, I guess. And now I bend my elbow. What's going to happen? Well, this region will look okay. This region will look okay. But in my elbow, something really crazy is going to happen, right? Which is that now I have a rectangle, another rectangle, and basically just a straight line gluing them together. And that's not so great. And so our solution to this problem, to make your skin essentially non-rigid, right? We aren't all made of porcelain, we're made of gooey stuff, is to attach a vertex to more than one bone at the same time. So in the middle of your limb, maybe you do move with the bone, but near the elbow, you're going to move as some weighted average of the upper arm and the lower arm. Okay, and so that's the basic trick in this skinning technique. Now, is this physical at all? Like, is this how the physics of skin and bones work? No, but it creates a nice motion. So let's see some examples of what that looks like. So a typical term you'll hear from artists in this area is something called skinning weights. These are we're going to talk about this more, but they're essentially the weights telling you the influence of a bone on the 3D surface. So here in this hand model, probably the skeleton looks something, like that along the fingers. Oops. Here's another one, and so on. I'm making this up. I don't actually know. And so the skinning weights are going to tell us which of the points on the outer surface are attached to which of the bones. So here we're showing you the colored regions are regions of points that are attached to a single bone. So for example, all of these light blue points are attached to this kind of upper finger bone above the distal joint. But the black regions are attached to more than one point. So what that means is that the way that we're getting this little curve here on the tip of this finger is by averaging the transformation of the bone on one side with the transformation of the bone on the other. Here's a second example, this time of a whole human. By the way, I think these were automatically generated skinning weights. So you can see that, for example, in regions like the upper shoulder, probably the motion is controlled both by your body and by your upper arm, whereas other parts of your body, like your lower arm, move more or less rigidly. So in order to describe that mathematically, we typically compute things called skinning weights or vertex weights. And these, in our class, we're going to call Wij. So the way to read this notation is how much vertex I should move with bone J. So J is going to index all the bones in my body. That means there's relatively few J's. Oops. Really wish that wouldn't happen. And there's going to be many I's, right? Because there are relatively few bones and lots of vertices on the outer surface. And so if Wij equals 1, for example, what that means is vertex I on my triangle mesh is rigidly attached to bone J. Okay? Now, you might ask, what sort of properties do these vertex weights have? And the answer is many. For one, essentially, we usually want our weights to be non-negative. I don't know what it would mean to have a negative weight here, typically. And the second one is that they all sum to 1. So in other words, essentially you can think of wij kind of like a weighted average, right? What it's saying is that like if I fix I and I look across all the j's, that's like how to average across the different bones to get my motion. Okay. Incidentally, if you're a mathematician, you might recognize these two conditions together. Doesn't really matter, but in case you're curious, these two things together define a mathematical object called a partition of unity. And indeed, algorithms that are automatically computing skinning weights, their basic output is a partition of unity. Our research group has actually worked on automatic skinning weights a little bit. So if you like these kinds of topics, please reach me out and I'd be more than happy to chat more. One thing, which is more of an implementation detail than a hard constraint, is that we typically limit the number of bones that influence a single vertex. I think this is a pretty reasonable assumption. I mean, the most crazy thing I could think of is maybe an octopus. But your body contains many bones. I can't think of a location on your body whose motion is like significantly affected by all of them. So we typically make an assumption that like relatively few bones influence a given vertex, like 4-ish. And this helps for a lot of things. So for example, if I have 100 bones, if I don't make this assumption, then I have to store 100 skinning weights with every single vertex on my triangle mesh. But here instead, I can just store sort of 4 index comma weight pairs, right? Like bone 3, bone 2, bone 1 has weight 0.3, 0.4, 0.3 or something like that. And so that's the typical way that you store it, right? Is the pairs of indices comma weights rather than just like a giant matrix of weight values. Okay, so hopefully you all understand the basics of a skinning weight. Remember, again, just to interpret that number one last time, the idea is that each vertex pi moves with some weighted combination of the bones bj, and that weight is given by wij. Okay, so those are what skinning weights are. Of course, the next thing we need to do is tell you how to actually use them. And so a different question you could ask is, given the skinning weights, how can we actually compute vertex positions in response to the motion of the bones in the body? And so that we're going to accomplish using a technique called linear blend skinning. So linear blend skinning is built on a few desiderata. So first of all, the basic idea that we're going to have is to transform every single vertex with every single bone. Now, this is crazy, right? Now, obviously, like my upper arm bone isn't going to affect my lower leg. But just for computational convenience for now, we're going to think of every single possible transformation as being carried out. And moreover, we're going to do it rigidly, right? So we're going to compute like the entire view of my body from my upper arm's perspective and so on. Then I'm going to use the skinning weights to select stuff out. So for example, if I know that wij equals 1, well, so what's going on is that I'd probably take the jth transformation applied to pi, and that's going to be the output for that particular vertex, right? Because that's the one that's moving. So the basic idea number 2 here is to blend the results of all of these possible transformations using the skinning weights. And so for the most part, stuff will move rigidly, right? What that means is that a vertex only has one non-zero skinning weight. But in regions like my elbow that are in between two rigid things, I can kind of smoothly transition from one rigid matrix to another. So let's write down an equation of what that looks like. So in particular, let's say that I apply basic idea number 1 here. Well, I can think of there being a transformation Tj, which is associated to bone j. Maybe I should put a j there. And use that to transform vertex pi. So if I do that, that will give me pij. We'll put a prime there. So prime will kind of denote like something moved. We can define that to be equal to Tj multiplied by pi. Right. So again, the Tj would be like the transformation of my upper arm, And then the PI would be like a vertex on my upper arm that has to move. Okay? So I'm going to do that for every possible pair. It's not terribly efficient algorithmically, but we'll talk about how to make it faster later. So that's step 1. And then in step 2, we want to take a weighted average using our skinning weights. So in order to do that, I want PI prime. There's no more J, right? Because at the end of the day, I don't care about the bones. I just want the pose of the mesh. And I'm going to do that by taking a weighted average. So I'll sum over all the J's, the weight of bone J on vertex I, times that vertex that got displaced in the previous step. Okay, so let's, by the magic of PowerPoint, here's a nicer version of the same math. So to reiterate, Pij prime is the vertex I transformed using bone J's transformation, where Tj is the transformation of bone J. And Pi prime is the result after taking the weighted average using weights Wij. All right, so let's take a look at what effect that has on a very simple model. So let's say that I have just 2 transformations. So this would be like the upper and lower arm example that we keep using here. And I have a vertex P naught, which is sitting right at the transition from the upper bone to the lower bone. So a reasonable set of skinning weights for P naught will probably be 0.5, 0.5, right? In other words, T1 has half the influence on P naught, T2 has half the influence on P naught. So let's see what happens to vertex P naught. Well, if I transform it just using P1, then I get P01 prime. That's what I've circled on the bottom. If I transform it using T2, I get P02 prime. And now I'm taking the weighted average with my skinning weights, and that is what leads to the true vertex position. So notice that originally my surface here was composed of 2 blocks that basically would intersect in a bad way if I moved every vertex with only 1 bone. But because I've taken this weighted average here, what I get is actually an elbow point somewhere in between. Now, if you stare at this picture long enough, you might say, but Justin, you've kind of cherry-picked an example here. In particular, what happens to the top of the arm? And you'd be absolutely right. So here's, let's say we mark a different point Q naught, and we want to know where it went. We'll notice that kind of a funny thing happened, which is like points here moved in, points there moved the other way. When I take the average, maybe I get some point like that. Notice that the width of the arm actually decreased at the elbow, which is a very typical artifact. This is sometimes known as the candy wrapper effect. And this is one of the basic issues that people try to fix in more advanced skinning algorithms. But for now, we're going to skip over that. We can summarize some techniques for fixing it later. Okay, so hopefully you guys get the basic idea here. Again, the basic point is that we're going to chunk up our surface and move every point rigidly. And then for things on the interface between 2 rigid parts, we'll move them with both sides. And then we're going to take the weighted average of the result using these skinning weights. There's a different question you might ask, which is where did the skinning weights come from? We'll also address that a little bit later today. Okay. So in order to do that, we need to make a few more definitions to fill in some details here. These are really critical details, by the way. One of them is something called the bind pose. So when I make a 3D model of my character, like this, whatever this dude is here, I have to model him or her or it in a particular, or them, in a particular pose. And so typically this is called the bind pose. So just by convention, oftentimes animated characters, especially human characters, the bind pose will be just like standing straight up, arms out. We find that that's sort of an easy one as a starting point for deformation. And so like when I download my triangle mesh of this character, that triangle mesh will be in that bind pose. And so you can think of the PIs as basically being in the object space of the skin. So like just like there's some base point inside of him somewhere, and all of the positions pi are relative to that global coordinate system. There's no hierarchy here, by the way, right? Like this is just a triangle mesh with a long list of vertices. But previously, we defined this object Pij prime as Tj applied to Pi. But in order for that expression to make sense, the coordinate systems have to kind of match up, right? So for instance, if I want to bend his arm here, well, then maybe I need to express Pi in the coordinate system of the arm, bend the arm, and then undo that motion, rather than somehow doing everything in the world coordinates sitting outside on the 3D character. So in order to do that, we're going to need to do a little bit more work. And here's how. So our undeformed vertices are in the object space of the skin, like just the 3D model that I modeled that is completely unaware of what I'm about to do with it deformation-wise. But the TJ is in some local bone coordinate system, right? That's like, so, and that is specified in the hierarchy of the skeleton, right? So I'd encourage you guys to revisit the previous lecture for how to think about that. So we need one more piece of information for SSD to really make sense. And that is basically what you get out of rigging. And the point is that in the bind pose of the triangle mesh, I also need to tell you where the skeleton is. And so this is sometimes giving you something called the rest pose transformations, BJ. And these are just sort of properties of the input 3D model, right? So oftentimes you'd have not just the 3D model, but also some information about how the skeleton sits inside of the 3D model. And what you get are these rest pose bone transformations, BJ, which go from, by the way, the from and the to are really critical here. They go from local bone coordinates to the global coordinates of the skin mesh. And so if you remember our previous lecture, you can obtain BJ by maybe concatenating a bunch of these hierarchical matrices, right? That go like from the base of the body to the upper arm, to the lower arm, to the wrist, and so on. And when you multiply all those matrices together in the right order, which is always the source of bugs, you get this matrix BJ. Okay, so now what do we do? Well, now we want to put this character in a new pose, right? He's bent his arms. Well, now we get a new matrix TJ, which goes from the local coordinate system of the deformed bone to the world space. Also, you can get that from concatenating hierarchy matrices. Notice you can basically reuse the same piece of code, right? So one piece of code composes matrices to get the rest pose, given the parameters of that. Then you just call the same piece of code, but with new joint angles to get the TJs, which are telling you the deformed pose of the skeleton. Okay, so now, essentially when we're animating our characters, what's changing are not the BJs, right? Those are the bind pose matrices, but the TJs, the bone transformations as this character is running and moving around. And so in order to deform a vertex PI, according to matrix TJ, we have to do two things. We have to take PI, write it in local coordinates, deform the local coordinates, and then undo it. And so that leads us to a formula like this. So here I take PI, that's in the coordinate system of the triangle mesh. I write it in the coordinate system of the bone in the rest pose, right? Because that's what the triangle mesh is in. And now I compose stuff in the other order to get this TJ. And that's what's going to give us the final Pij prime. If you're looking for sources of bugs in your code, you're staring at them here. There's two things that I think are very typical to get wrong on your homework. One is the ordering. Does TJ go first or does BJ go first? And which one is the inverse? So again, remember, I think 2 lectures ago, I advised you to think about matrices as like little functions of code. Like, for instance, notice I was very careful to tell you that like B goes from local bone coordinates to global, right? So B inverse goes from global to local. And then T goes back out to global, but in the deformed pose. So these are in the right order. If you're wondering, your instructor always gets this kind of stuff wrong. So you're in good company if your code has a bug. Okay, so that's it. This is our really key formula for Pij prime. And the good news is that we can compute this this vector really quickly in parallel, right? So remember, your computer graphics card inside of your computer is really good at just like carrying out the same calculation a million times with like a different point. And this is a good example, right? Because for every single ij pair, I just need to multiply 3 matrices together, or I guess 2 matrices and a point. And that's the kind of computation that you can do massively in parallel, might be the phrase we would use. Okay. So, right. So let's think a little bit about this formula. Which essentially is mapping Pi from the bind pose to the local coordinate system of bone J and then to the world space using Tj. Now, I can parenthesize this expression any way that I want. I think so far when we've talked about it, it's been kind of like that, right? Like take Pi, apply this thing, then apply this thing. Instead, let's parenthesize this expression in a slightly different fashion. In particular, I'm going to write it like that. So notice that this thing is a function of j, and this is a function of I. Okay? So in this setup here, if I group in this fashion, let's put a box around it instead for fun. You could ask, what is this matrix, right? It's kind of composing 2 different motions. And we tell you what it is right down here. This is the relative change between the bone transformation of the current and the bind pose. And if you think about it, that makes perfect sense, because when you're deforming your animated character, essentially what you have to do is compensate for the difference between the pose you want it to be in and the pose you have it in your input mesh. So let's say that I gave as parameters for my bones the parameters of the bind pose. Well, in that case, T and B would be the same. So when I multiply these 2 things together, I get the identity matrix, which makes sense, right? Because it would take in the skinned triangle mesh and just give us back the original vertex positions. Okay, so that gives us the Pij primes. Remember that in addition to that, we have these Wij weights, and we use those to compute a weighted average. That gives us our final vertex positions. One fact, which is a bit of a downer as a computer graphics researcher right now, a very well-studied problem is the automatic computation of skinning weights. Unfortunately, these tools are not terribly popular in practice, so it's still pretty common for artists and animators to paint skinning weights by hand, and there's all kinds of nice tools and software like Maya for doing that. In some sense, I would view this as a bit of a failure of the technology community, right? Like, essentially, we're making the artist the slave of our animation algorithm. And so I think there's some really great motivation here to improve these techniques, maybe incorporating both some ideas from differential geometry and smooth, math with machine learning, because both of those matter here, right? In order to have an intelligent algorithm for computing skinning weights, you simultaneously, for one thing, want to know like what a partition of unity is, what it means to be a smooth function, but you also want to know where the arms and the legs are. And so it's a great sort of interaction between a lot of different challenging topics. Okay, so if we want to summarize a little bit, here's our pseudocode for doing skinning. So we'll do our forward kinematics, and that is going to give us this matrix Tj per bone. Again, remember that forward kinematics is basically just a fancy phrase for what we did in the previous lecture, like composing this hierarchy of transformation matrices together. And this is going to give us the full transformation from local coordinates to world coordinates. Or if I invert, it'll go the other way. Then every skin vertex Pi gets transformed to Pi prime using the formula that we've written here. This is just a giant for loop, right? So I'm going to sum over all the bones, take the weighted average, and perform the transformation that we've talked about over the last couple slides. And this is going to take us from the triangle mesh to its deformed pose. Now, one thing that we should remember from previous lectures. Essentially, what are we doing? Well, we can factor this expression any way that we want. There's no j dependence on this very last term here, so maybe I parenthesize it like that. Right? So you can think of this object as the matrix that's being applied to pi at the end of the day to compute the pose of the skinned triangle mesh. So remember that if M is the matrix that's being applied to deform a shape, how do I deform its normals? Well, for a bit of review from our previous lecture, remember that that's M inverse transpose. Yeah. So typically a triangle mesh is actually stored with one normal vector per vertex of the triangle mesh. Later in this course, when we talk about rendering, we'll see why. So what that means is in our skinning algorithm, we have to do two things. The first thing we have to do is actually deform the mesh. The second thing we have to do is deform the normals. And in order to do that, we need to apply a different formula. So again, this is just a little bit of review. Just remember that you can't use the same matrix to transform your mesh as you can to transform its normals. They're inverse transposes of one another. Okay, so a few more things to note. One is that typically the weights and the bind poses are constant over time, right? Those are like painted by the artist ahead of time. So the only matrices that change are these TJs. So there's actually a lot of opportunity here for pre-computation. In fact, you can do a lot of this computation in a GPU Vertex shader. A Vertex shader is like a little tiny piece of code that you can run per vertex on a triangle mesh. Typically, your graphics card knows how to do that really quickly. And so that's typically where skinning is implemented. What that means in practice is that this SSD algorithm that we've just covered is actually totally feasible to implement inside of a real-time graphics pipeline. This isn't just an effect that like the fancy high-end movie studios get to use. Okay. So now let's think about some drawbacks of this really simplistic algorithm. I mean, this is like computer graphics circa 1990. Now, remember this on the top of this slide, this is our formula for how we're going to deform vertices. And here, all I've done at the bottom of the slide is insert two parentheses, and that gave us the formula down here. The question is, what the heck is this matrix? Now, we would probably think of the matrices that we want to apply to these human characters as being pretty much just rotations and translations, right? It's not like your body is compressing all that much when you deform. And so you might expect this matrix to be a rotation, but this is actually not quite what typically happens. So this matrix here, this might be a rotation and a translation, but then they're getting averaged together. Okay, so let's think about different rotation matrices. So here's a really boring one. This rotates by 0 degrees. Let's just do it in the plane. Rotation by 0 degrees is also known as the identity matrix. 1, 0, 0, 1. And let's say that I rotate by 180 degrees. Now, hopefully I'll get this computation right. If I don't, I'm sure I'll hear about it on Piazza, which is fine. But if I rotate by 180 degrees, what's going to happen? Well, the x-axis becomes the minus x-axis. The y-axis becomes the minus y-axis, like that. So let's say that I took my arm and I folded it 180 degrees. I want my arm to basically just be, completely bent. Then I'm likely to do a computation like what we see on the bottom of the slide here. And right at the center of my elbow, this parenthesized expression that I've drawn all over, right, this guy, is going to be the average of these two matrices that I've given you on the side of the slide. Now these are two rotation matrices. That part is okay. But when I average them together, right, so this is R0 plus R180 divided by 2, what do I get? I get 0, 0, 0, 0. Is that a rotation matrix? No. So that's where SSD is a bit of a hack. This method is averaging transformations, and averaging matrices has some really weird effects. Like if I average rotations together, I don't get a rotation. And that's what's causing these crazy effects. So like I mentioned before, this is called the candy wrapper effect. You can already see it here, right? Like the width of the arm is different than the width of the bicep or the forearm. Or if your character rotates in the other direction, then you really see it, because then you can get closer to this 180-degree effect. Lots of work in research and engineering has gone into how to counteract this effect. I think you still see it in some video games if you look close enough. One is to use the quaternionic representation of rotations, which turns out to have some nicer properties when you average. Or maybe you average and then project back onto rotation matrices or something else. But all this is to say the SSD method, which is the one that you're responsible for in 6837, is just like the tip of the iceberg. And there's so many other approaches to these problems that can get better results. Now, I mentioned to you guys that skinning is typically done by an artist by literally painting them on. There are automatic tools out there, and my bet is if I keep teaching this course in this age of machine learning, we'll see many, many more. We might want to try and find skinning weights, for example, by optimization. So maybe I am willing to take my original bind pose and then give you a few more examples of poses. Whatever. I'm not a very good Madonna here. But in that case, given a few different poses, I could try to write optimization code that infers the skinning weights given those different examples. Or I could even try and transfer skinning weights in motion from one reference model to another, right? So one of the sort of classic techniques for this all the way back from SIGGRAPH 2007, which originated at MIT, was this automatic rigging and animation technique, which can sort of allow us to make different animated characters that can move in lockstep. And so the system that they made, they called it Pinocchio. Let's see if we can play a demo of what that looks like. I'm not sure if my laptop will be able to handle it. So here's our character. Here's an animation sequence for a skeleton. Here's the skinned animated sequence. And now, using tools like this Pinocchio method, this one is relatively guided by a lot of manual intervention, but that was understandable because it was a while ago. You can see that we're essentially taking the same sequence applied to the skeleton and moving lots of different animated characters around all in lockstep, which I'll admit your instructor finds a little bit terrifying for this particular animated sequence. Okay, so to recap a little bit for the end of lecture today, we covered a few different strategies for computer animation, including keyframing, procedural animation, and physically based animation, just the terms. And roughly in this course, we'll try to cover a little bit of each. And we talked about how people might define high-level controls for the animation procedure. In particular, two vocabulary words you should be sure to remember are forward and inverse kinematics. Right? So forward kinematics controls an animation by like giving the joint angles and then inferring the pose of the character. And inverse kinematics does the opposite. Like I place my hand here and it figures out the joint angles that try to accomplish that particular pose. Then we spent the last part of our lecture talking about a particular technique for character animation that allows us to animate a skeleton and then move the skin of a triangle mesh with it. And that's this SSD technique. And at the end of the day, this really boils down to two big ideas. One is computing or using skinning weights to average different rigid motions together. And the other is keeping track of deformations really carefully. Right, that product of T and B and making sure they're in the right order to actually get the motion that we want. So that'll do it for today. And when we continue, we'll basically pick up where we left off and continue to talk about new methods and more methods for computer animation, including some that you'll implement in your homework.